in this case, you see, again, very good agreement for all phases of the motion. And I show you, again, the video for this motion right here. And the important thing to notice here is how the positive vortex now has moved to the top and the other one to the bottom. And you can see how there is, if you can do an integral with your eyes, you can actually see how now there is this kind of jetting flow, like even in between vortex structures, there's still a net velocity forward. And this is how the thrust is produced. Again, we compare with the model with the data, and we get good agreement. Okay, now with this good agreement, our next task was to actually see if we can also predict the force. In this case, this is the streamwise coefficient of, or the coefficient of the mean streamwise force acting on the airfoil, which could be either drag or thrust. This is calculated from applying the integral momentum equation on the airfoil. It's very simple. You have the airfoil is here, put a box around it. We will imagine that the top and bottom are at infinity. Then we have upstream and downstream boundaries. There's uniform flow coming from upstream, and then downstream we have whatever we can predict with the model. Now, there's something that I would like you to pay attention to here and remember for the rest of the talk. There is 3 different components in this integral that gives us CF. The first one, which is the one that you have probably seen in your undergraduate fluid mechanics, is just part of the mean velocity in the wake. And in many cases, you know that people actually compute drag on an object with the assumption of 2 dimensionality. You take a pitot probe in the wake, you do a survey, you get the mean velocity, and then you actually get this, you can calculate the drag or the force acting on the airfoil from this term. Notice how this term can be negative, which is drag if there is velocity deficit, or can be thrust if there is velocity excess or jet in the wake. Now, in many cases, you're not going to see these terms when people apply this equation. And part of the reason for this is that if the airfoil is stationary, or if the object is stationary, the RMS fluctuations are generally small compared to the mean velocity. Now, one thing I failed to mention is that if you look at these RMS levels, you look at this VRMS normalized by U infinity, you're actually approaching U infinity. In fact, if you had paid close attention to these videos, instantaneously for this particular case, there was complete velocity reversal at one point. So this vortex structure are able to induce, they're so strong, they're able to induce flow that even reverses the flow completely. So because of the intensity of the fluctuations, then you have to include these in the calculations. And then this is what we would call the fluctuating field term. So there's net force because of the mean field, and there's net force because of the fluctuating field. And very important to notice this term here, look at this is a positive definite term with a negative sign in front of it. So this term can only produce drag. So the larger the VRMS fluctuations, the larger the drag is on this airfoil as well. And in fact, we call this pressure drag because you can convince yourself if you use the integral momentum equation in the cross-stream direction that in fact this is related to the pressure gradient in that direction, and hence it is essentially the low pressure core of the vortex structure. The stronger a vortex is, like a tornado, you produce a low pressure core inside it. You get low pressure, and that produces a net pressure drag in your integral momentum analysis. So remember, this CF is really what you care about ultimately, but it has 2 important components, one from the mean field and this mean pressure term here. Here's a comparison between our calculations, and in this case, remember, we have only 3 cases which are shown in the solid triangles over here. We are actually showing in red the CF mean by itself, and in blue the complete CF. Now, the first thing I would like to notice in comparison with these different experimental and computational data, that in fact the model does a good job of predicting within the scatter of the data the results that are measured and computed. And that gives us confidence in using this model for calculating the force. In addition, notice how this is the mean CF, but the net CF actually is below the mean CF, and that's because of this pressure term, that VRMS term. And because this VRMS term actually dominates the URMS, so it's always stronger than the URMS. Now, having this validated that our model does a good job of predicting the velocity field behind the airfoil, then our next step is actually to do some parametric study and actually look at how these different, if you vary the wavelengths, the B, the circulation, how these different parameters actually relate to the force acting on the airfoil. So the first thing we're going to look at is the B effect. So what I would like you to remember is that B is the lateral spacing between the two different sine vortices, and we fix everything else in this model. The only thing that we're changing is the difference between the two. What I'm showing here is the mean streamwise velocity across the wake, starting from the neutral condition. So B over C is 0, the centers are on the center line. And you keep increasing the B. As you increase the B, frequency is the same. You actually start to develop this jet profile also. And the bigger the B is, the jet becomes stronger as well as wider. Eventually, beyond a certain B, this profile actually becomes plug-like or slug-like flow. It's a top hat profile where the peak of the velocity does not change anymore, and instead the width of the profile actually keeps getting bigger and bigger. Now, if you look at this condition, when you reach this condition, then it looks like you have this strong shear variation over a very thin zone on top and another one on bottom in this uniform profile in between. And if you think about fundamental aerodynamics, you realize this essentially is nothing more than two vortex sheets. A vortex sheet is a different concept than a vortex. An idealized vortex sheet like this is a distribution of vorticity over a line. And in this case, you cannot simply characterize it by circulation, but because of its continuous distribution, you characterize it by circulation per unit length. Okay? And that's why we use the small gamma. So it's like, you can think of it as circulation density, if you wish. And the summation, if you put two vortex sheets like that, each one, the induced velocity will have this kind of jump that is related to the small gamma, so that the full jump is actually of magnitude gamma. And with spacing B, when you add the two, you essentially get something that looks exactly like what we have here. So if you look at that and you take a clue of this, then you say, okay, I understand that I don't actually have a continuous distribution of vorticity. I have a vortex, 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 vortex. But then you say, okay, what if I calculate the equivalent circulation per unit length? So I take my gamma from the vortex and divide it by the spacing A, and call this my small gamma for my model. Then I have, here's my gamma, 0.4, divided by 0.4. That's actually a 1, and this is exactly what this jump is. So in fact, this, even for this kind of discrete model, this actually holds well in this case, provided that the B is far enough. And what the nice thing about this is, because this profile is easy to integrate in the integral momentum equation, and you can actually get a simple expression for the CF mean in this DSL is what we call the vortex sheet limit, which is high B limit. And in fact, since our gamma can be replaced by this, then we can, the actual force produced by due to the mean velocity can be calculated from the simple equation where we can see there's in fact linear variation with B. So one thing we can do is we can use this as a simple model for CF mean and compare it. If we take each one of these cases and then do the calculation of CF mean and full CF for it and compare it against the simple model and see how these two compare. And if we do that, then you have this linear trend shown by the line, which is the vortex sheet limit. So this is CF versus the B over C. And you can see that in fact, as what we would expect, that the solid symbols, which are the actual CF mean, they agree well with the line, at least visually. And the full CF itself is not that far from it. So even for large B over C, even the full CF is actually, we have not such a bad approximation of it with this very simple model. Now, one thing that you might start to think about is that, okay, well, we saw that if B over C is large enough, then you get this slug-like profile, which is should be described well by the vortex sheet limit. However, at low B over C, we don't have that. We have more of like a Gaussian type profile. So why do you have what looks visually like a good agreement over here? In fact, it's not as good agreement down here. If you look more closely, if you actually divide the CF mean by the vortex sheet limit, which is the dashed line, you can see it only really approaches that asymptotically. So the first 2 points are, in fact, do deviate a lot more than the ones that are larger B over C. So, but the main lesson here that we learned is that as B over C goes up, that's actually good for increasing the thrust. Another effect we'll look at is the circulation effect. Again, if we just focus on the CF mean first before we look at the full CF, for a particular choice of B over C and A over C, you can see as gamma increases, the CF actually increases. In fact, it increases parabolically, that we, in the remainder of the stalk, a continuous line like this would be used for the CF mean. This is intuitive because remember, as the vortex induces this jet-like profile behind the airfoil, so the stronger the circulation of the vortex, the stronger the jet behind it. So that's intuitive, so that's good. Now, if you, and I would like you to remember this fact. Now, if you actually make the, this is exactly what you see over here. So I'm just showing the velocity profiles for each one of these 4 cases that we actually calculated. Now, if you do this calculation, however, for a different wavelength, then you see that as the wavelength increases, so the spacing between the vortex structures becomes longer and longer, then in fact that CF goes down for the same circulation. So in that sense, longer wavelengths are not good for the production of thrust for the same circulation. Now, remember, all of this is in fact for just the CF mean. Ultimately, we care about the full CF. So if we, for the 4 cases we calculated for the model here, if we impose, let's not worry about this, if we impose the full CF, so the symbols here with the same color correspond to the full CF for the particular case, and we can see that at long wavelength, that more or less follows the CF mean. However, as the wavelength becomes more and more, the full CF drops quite a bit below the CF mean. And the drop itself is not too bad. What's really bad is that when you go to really long A over C, look what happens. Actually, for this black case, for example, eventually this CF actually starts to go down with circulation. So we're making the vortex structures stronger, and as we agreed before, that creates more thrust, but now it starts to create less thrust. And the reason is, remember, as the vortex gets stronger, it's true that you get this induced flow becoming stronger, but remember, V component, or VRMS also of the vortex becomes stronger. The faster the vortex spinning, the lower is the pressure in the core and the lower is the pressure drag. And the balance between the two becomes in favor of the pressure drag at these long wavelengths. And I will show you this kind of non-monotonic dependence. So that's one important fact here, is the non-monotonic dependence. And the other thing that I would like you to note is that the drop because of the CFP seems to be largest for this green line here that goes more down for this intermediate wavelength. And these 2 observations, I will clarify them on the next couple of slides. So first, let's deal with the non-monotonic dependence, and for this I will focus on the black and the blue case over here. And if we look at this and magnify, so this is just a magnification of the plot that I just showed you. You can see initially the CF follows the trend that we expect where it goes up with gamma, but then eventually you get this non-monotonic trend where it goes down. You can actually see this because if we now pay attention to the VRMS, so this is VRMS now, which produces the CFP, the pressure drag, you can see that as the wavelength as the gamma increases, that in fact VRMS not only becomes stronger, but it becomes wider as well. So more pressure drag. And in fact, if you compute the CF mean versus gamma from just the CF mean by itself is over here, just the CFP, which is the pressure drag coefficient from over there, you can see how initially this is rising at a faster rate and overcomes the CFP, but eventually this one actually takes over. So this up here is bigger than this over there, and the net effect is actually is opposite to what you expect. Finally, as far as the model analysis is concerned, we also look at this YCFP is worse when the wavelength is intermediate somewhere in between. So for this 4 different wavelengths that we calculated, this is the CFP, and you can see it's negative, of course, because it produces drag, and it's worse somewhere in the middle over here. You can actually see why you have this non-monotonic trend, because to understand CFP, we look at the VRMS profiles. For this small a value, you have a profile that has this kind of distribution. You increase it to this one, which is the green. You can see how VRMS becomes stronger, and then it becomes wider, so that's larger drag. You increase it over here, then you go to this blue line, which now the peak actually goes down instead of going up. It's still becoming wider, but the peak is actually, the level is becoming less, so that the net effect is less drag. And finally, you get to this one, and it even goes down some more. Now, we can explain this in terms of the actual profiles of the velocity on the center line, which I will skip for the moment because I'm running out of time, but I'm happy to talk to you about why this happens. In the next 3 slides, I will just very quickly demonstrate that the model also works for the non-harmonic oscillation. In this case, this is the actual angle of the airfoil. So the red one is just sinusoidal going up and down between the 2 degrees. This blue line, we actually increase or shorten the pitch up time. So the airfoil is actually going up faster than it's coming down. So the time of the pitch up, meaning going up like this, as a fraction of the cycle, instead of being 50% for the symmetric oscillation, it becomes 38% of the symmetric oscillation. Okay? Now, to your eyes, that looks like a very subtle change, like not very much deviation from symmetry. However, if you look at the wave structure, it's completely different. Not only it's not just 2 pair or a pair of counter-rotating vortices shed per cycle, you actually get 3 pairs of vortices shed per cycle. You have 2 of these that have the same sign and 1 that has an opposite sign. And in fact, because of this configuration, see how the relative positioning of the vortex structure changes as they convect downstream. So it's the mutually induced velocity between the vortex structure causes them to change orientation. So this creates kind of a difficulty because remember, if you are going to set up a model of the structure, you hope that it's not changing with downstream distance because then you can apply it anywhere you want. Here, the configuration of the vortex structure changes with downstream distance. The particular measurements were done in this particular case where you have negative, negative, and then positive one. So that's the configuration that you will see us model. But the interesting part is that even though as you travel downstream, it's changing, the configuration is changing, we're actually going to ignore that, and we're going to just simply in our model take the shape in the vicinity of our measurements and just duplicate that. Okay? So that's exactly what you see. You have the negative, negative, positive, negative, negative, positive, etc. There are more parameters in this case. And this is the agreement that you get, which is still quite good, especially with the fact that, in fact, you're making an assumption that it stays the same, that the pattern. But the reason for this is, in fact, this Biot-Savart relation that we looked at. If you notice this, you will see that in the denominator of this relation, there is a division by the distance cubed between where the vorticity is and where you're calculating the velocity. So in fact, the effect of faraway vortex structure decays, in this case, fast enough that it's not that important that you actually duplicate it exactly. And something that's quite interesting as well is that the statistics comparison, mean RMS and VRMS, sorry, this is not a comparison, is actually very good. And what I would like you to imagine if you go to the lab and you actually measure this kind of RMS distribution. You wouldn't believe that this is the real thing. It doesn't even look anything organized. It looks like it's varying randomly. But in reality, it has a very organized structure behind it. And the model helps you exactly understand why it looks this very strange way. And finally, I will show you the video of the entire calculation. And you can see that the velocity field now instantaneously is much more complex. But again, as each vortex goes by, you can see how you get this high shear produced in a direction that's consistent with the vortex sense of rotation. And the net effect of these variations is exactly what you see in the RMS fluctuation. So with this in mind, basically, I reached the conclusions stage. So we have demonstrated that such a model, which is very efficient, I mean, you run this, in just a few minutes on MATLAB. You can calculate, you can compute the wake velocity field, you can calculate the forces out of that. In terms of measurements, this obviously is a good step towards having a design tool for calculating thrust. But in addition, as for an experimentalist, if you have only single velocity measurements and a periodic flow that is dominated by vortex structures, not necessarily just that. Potentially, it could be some turbo machine that has still a well-organized vortex structure behind it. Then you can use a model like this to extract information beyond what you're measuring. Whatever the limited set of data you have, you can use to make sure that the model is actually working well. Once you have that confidence, then you can use the model to get additional information. And I will not go into this, it's a bit more detailed. These are just the different effects of gamma A and B that I went over, and that gives you some sort of a net conclusion. If you want to maximize the thrust, then this is the sort of direction that you want to vary these parameters in. So with this, shukran. أستمعكم. I'll be happy to. أنا خريج 85 بس.
أول عارف.
حضرتك درست لي طبعا internal combustion engines.
أنا بس عايز يعني معلومات متواضعة إن ده هايبربوليك فلو.
أوكي.
طيب فين السونيك سبيد في الموجود؟
لا this is actually elliptic. It's not hyperbolic because this is an incompressible flow, and this is a low Mach number flow. Yeah, this. I missed يعني the problem we're dealing with is this is what we're dealing with is basically flyers, naturally like birds and insects. So so we're dealing with incompressible flow. These are all low Mach numbers.
Subsonic flow.
Huh? So it's, you know, this is like birds that, you know, fly as you see outside and insects, so it's all subsonic.
I think if you want to the higher speed, you have to go to jets. Jet fluid related.
هو
Because it'll be higher velocities.
هي البروبلم اللي هي ال compressibility effects become important for is the helicopter
Yes.
problem, which yeah, this is something we didn't do because the helicopter will have this you know, periodic pitching as they go around as the rotor blade. بس احنا يعني we have not been concerned with the high speed. وحضرتك عشان ما شفتش دي من الاول فانت فاكرنا بنعمل تمام.
طب مش المفروض دي اساسا يعني المفروض ما نلعبش فيها دي انا بحاول اقربها للواقع عشان تبقى اعمل موديلنج للواقع مش انا المفروض اقدر العب فيها يعني هي دي نتيجه مش يعني في حاجه اوصل لها مش
هو ده سؤال كويس. اولا انا ببقى عايزها تبقى زي الواقع لما انا بقارن بكيس معين. وده فعلا في الجزء الاولاني لما كنا بنعمل مقارنه ده فعلا كانت زي الواقع. بس بعد كده احنا بنقول ايه؟ طيب احنا بقى عندنا موديل that represents the physics. انا عايز ابتدي اعرف ايه الريليشن بين البارامترز دهيت والفورس that is acting on the airfoil. لان انا لو فهمت كده يبقى انا ممكن استخدم الحكايه دي مثلا as a control scheme. يعني اقول هل انا ممكن ان انا اعمل حاجه في الموشن بتاع الايرفويل. يعني انا مثلا عرفت من الحاجات اما كنا بنغير البارامترز ديت عرفت ان انا عايز الويف لينث ما يبقاش شورت قوي وما يبقاش يبقى شورت ما يبقاش ميديوم اور لونج. فانا ممكن اعمل حاجه في التراجكتوري اوف ذا موشن بحيث ان انا اغير الاي دهيت in a favorable way. فانا بستخدم الموديل اللي انا عارف ان هو بيعمل description للفيزيكس ان انا to explore البارامترز دي لما بتتغير يبقى ممكن تعمل لي ايه. فهو كانه سؤال عكسي. يعني انت بدل ما تقول خليني اعمل اوسيليشن للايرفويل بالشكل ده و I get what I get. طيب انا دلوقتي عايز اعمل wake vortex pattern معين بايه معينه بي معينه جاما معينه. فالموديل يساعدني ان انا اعرف ده هيعمل لي ايه في الفورس وبعدين انا هبقى احاول بقى افهم ايه التراجكتوري اللي انا عايزه عشان يديني الحاجات دي.
ازاي ما تجيبش ريليشن بالعكس يعني ما تجيبش ريليشن ازاي اجيب الاي والبي يعني مجرد اقول لو كان عندي اي والبي دي كنت وصلت لكده. ده يعني الموديل بيقول بيعمل كده صح؟ يعني ما بيقولش ان انا اوصل للاي والبي دي ازاي.
دي برضه نقطة ممتازة. عشان كده أنا لما قلت في الأوبجيكتيف قلت يعني this is a step in the direction of actually having a design tool. لأن في النهاية لما أنت بقى بتتكلم عليها من ناحية الديزاين مش من ناحية الكنترول من ناحية الديزاين أنت فعلا أنا هقول لك أنا عندي ايرفويل بتعمل موشن معينة أنت عايز تعرف to predict ال A وال B وال جاما عشان تقوم حاططهم في الموديل ويديك الفورس مظبوط. فاحنا دلوقتي الابحاث اللي احنا شغالين فيها دلوقتي we are actually focusing يعني we're using whole field measurements and we are focusing بالظبط على الحته دي. فلما عندنا high resolution measurements ولما as the airfoil oscillates we're looking at the details of the boundary layer, how it separates and how it rolls into the vortex structure. Our aim is to hopefully understand the physics of vorticity shedding and how this vortex flux maps into the vortex pattern and relate this to the motion of the airfoil. لو احنا كان عندنا الميسنج لينك دهوت يبقى نقدر بقى ناخد a given profile and you know as I said يعني I was careful in my statement. I said this is a movement in a step in the right direction.
طيب نعمل ايه لو كان في بعض الموستشر؟
بعد ايه؟
موستشر رطوبة.
يعني two phase flow. يعني you have to use two phase flow equation يعني
لا يعني
بس هي الموشن
هنا
لا مفيش
ايوه انا عارف اهو.
ما هو it's air properties يعني
الرفوت بتاع جناح طيارة
ما هو المفروض طاير في الهواء يعني. بس same concept.
درجات الحراره الواطيه بيحصل فريزنج للموتشر.
I mean, this is a practical problem. يعني this is يعني freezing of moisture and قصدك accumulation of on the بالظبط يعني they wing الطيارات عليه بيعمل de-icing كده هوت يعني. This is a
كولينج
practical.
وفيلم هيتنج بقى فيلم كولينج وفيلم هيتنج.
يعني this is a different problem. ان انت you're dealing with a more practical problem. إذا كان عندك ice accumulation طبعا that will change the shape of the airfoil and will change the aerodynamics. فهيحصل هتتغير حسب بقى الشيب يعني you have to deal with the shape in this case. But one thing I should say is that